All right, so now that we have, in section 2, we learned about parametric equations. Now we're going to apply calculus to our parametric equations for section 3. So today's objective is parametric equations and calculus. Well, the first thing that we learned when dealing with calculus is our derivative. So obviously we need to know how to take the derivative if it's a parametric equation. And we know that our derivative tells us the slope. It can find us the equation of a tangent line. It can tell us about concavity. Lots of information that we get from our derivative. So by definition, if a smooth curve C, so we know that that smooth curve represents a parametric equation, is given by our equations x equals f of t and y equals g of t, then the slope of C, so C is our smooth curve at our point xy, is given by this. Well, we know that derivative means change in y over change in x. In this situation, we know that we're going to be, both of our equations are in terms of t. So what this means is take the derivative of y with respect to t divided by the derivative of x with respect to t. So it's super easy, because then it's just this equation, your y prime is in the numerator and x prime is in the denominator. So really nice. And we know that the derivative can tell us the slope. Well, your slope is rise over run. So you rise with your y's, you run with your x's, and that's why you rise over run, and change in y over change in x. The second derivative is a little bit goofy looking notation, and remember that this can tell us about the concavity of something, or of our curve. And notation looks like this for second derivative. So we have our second derivative, and this is y, because our equation is y, divided by the derivative of x squared. Well, we can break this notation up and say we're taking the derivative with respect to x of differential y with respect to x. So that's how this notation comes that you have if you distribute this through, because this tells us derivative with respect to x. It doesn't tell us what specific variable. And now here, when I say take the derivative of the derivative, obviously that's second derivative. Well, what this comes up, or what this is equivalent to, we know that these things are going to be in terms of t. So because up here in our first derivative, the derivative of y is in terms of t, the derivative of x is in terms of t. So we still need our derivative in terms of t. So this breaks it down, and here we're taking the derivative of this, of our first derivative, basically, and that's in terms of t. Well, now we have to also, if we're going to take the derivative of the denominator in terms of t, and our denominator, we just have a differential of x left. Oops, so then this, because this portion of it all went to the numerator, and now we have this differential of x we still have to deal with in the denominator, so that makes it look like that. It's a little bit goofy when we do an example. It's pretty easy to follow. So we have two examples here. We first of all need to find the slope and concavity of our given value, or at the given value of the parameter, and then find the equation of our tangent line. We want our answer to be in rectangular form. So for number 8, our parametric equation, x equals t squared plus 3t plus 2, y is equal to 2t, and this is when t is equivalent to 0. So that is the specific time that you were trying at, when it says the given value of our parameter, that's when t is equal to 0. All right, well, slope and concavity. Slope is incredibly easy. Change in y with respect to x. Well, your change in y is just 2. The change in x is 2t plus 3. So super easy to take our derivative. Well, now we can find the slope at our given point. So if t is equal to 0, our slope is going to be 2 divided by our 2 times 0, 0 plus 3. So our slope is 2/3. If we have to find the concavity at this given value, then we need our second derivative. So concavity And second derivative, so that tells us we need, this is our notation for it. How this breaks down is really, it's your, in the numerator, it's the derivative of your first derivative. So if I have to take the derivative of this thing, I would use the quotient rule because there's no great way to simplify it, and oftentimes you will end up using the quotient rule because you have a fraction here. So if we take the quotient rule, the derivative of the numerator is 0, times our denominator is obviously 0. Then we're subtracting the derivative of the denominator, which is 2, times the numerator, which is 2, all divided by our denominator squared. So that's just the quotient rule in the numerator, and I get it from it's the derivative of the first derivative, which would mean second derivative. Then the denominator, it stays as 2t plus 3. And why that happens, if you look back up at the notation, it just says it's the derivative of x with respect to t. Well, this derivative of x with respect to t, all we do is take your x equation, here's our x equation, and take the derivative of it. Where in this notation it says, we're taking the derivative of our first derivative, and that's why the numerator is the derivative of our first derivative. I think these just take a little bit of practice, just getting used to that. I guess how that all works out. Now we can simplify this if we want to, but don't simplify too much and make it real crazy. But here I can say it's a -4, and instead of dividing, I'll put it over 1. Instead of dividing, I can multiply by the reciprocal, which would create 2t plus 3 cubed. And you, again, if we just want to know about the concavity of it, whether it's concave up or concave down, you don't have to do a lot of simplifying. We just have to know whether our answer is positive or negative. Well, now if I plug in a 0 into this, because remember this is where when t is equal to 0, then we know that our concavity is equivalent to, our numerator would be -4, our denominator, plug in our 0, would give us 3 cubed, which is 27. Well, that's equal to a negative value. Therefore, we have that this is concave down. So pretty basic, and really the exact value of it doesn't matter. It's whether it's positive or negative. So going back, we found our slope, we found the concavity. Now we have to find the equation of our tangent line. All right, and we want this in rectangular form, which is nice because that's just our x and y. Well, in this situation, if our parameters at t equals 0, we know then our slope is 2/3. So here we can say, well, when t is equivalent to 0, our slope is equal to 2/3. And what's the last thing that we need in order to write the equation of a line? We have a parameter, we have our slope. We also need a point. Well, to get our point is very easy. You plug your parameter into your equations. So if t equals 0, plug it back into your two equations. So plug it into for our x, plug it in for our y. If t is 0, we have 0, 0, 2. We're adding those together, obviously. And for our y's, if t is 0, we'd have 0. So now we have our point at 2, 0. I like to use point slope form to write the equation. So I have y minus 0, well, I'm not even going to put in the minus 0, is equal to the slope, 2/3, times x minus my x value, which is 2. Now I can clean this up a little bit. So I have y equals 2/3 x minus 4/3. And there is the equation of our tangent line in rectangular form. One more example like this, if we have trig instead. So we have to first find our derivative in order to find slope. So dy over dx, the derivative of y is going to give us, the derivative of 1 is 0. The derivative of negative sine theta would give us a positive sine theta, divided by 1 minus the derivative of sine cosine theta. In this situation, it's when theta is equal to pi. Therefore, our slope is sine of pi is 0. 1 minus cosine pi is -1. And really, I know we have 0 in the numerator, but we just have to ensure that the denominator is not 0. So we have 0 divided by 2. Great, that's not an indeterminate form. We have an answer of 0. So our slope is 0. If your slope is 0, what does that tell us? At this, when theta is equal to pi. Remember, it tells us if our slope is ever 0, we have a horizontal tangent. So that indicates that we have a horizontal tangent. Second derivative, which will indicate our concavity. Take the derivative of the numerator. Or, I'm sorry, the derivative of our first derivative for the numerator, which is kind of ugly. And again, like I said, you're almost always forced to use a quotient rule because that first derivative is going to be a fraction. So the derivative of sine is cosine times the denominator, 1 minus cosine theta, minus the derivative of the denominator. Well, the derivative of 1 is 0. The derivative of negative cosine is going to be a positive sine. And now I'm multiplying it by the numerator. So if I multiply it by another sine, I have sine squared. Didn't give myself a lot of room here. This is all divided by our denominator squared, so using our quotient rule. Now we have to divide again by just the derivative of our x. So 1 minus cosine theta. Well, if we clean this up a little bit, I'm going to distribute, so I have cosine of theta times 1, and well, that's cosine of theta. In this one, distribute, that would give us negative cosine squared theta. And then we have minus sine squared theta. And again, when you multiply by the reciprocal of your denominator here, instead of dividing, multiply by the reciprocal, you get 1 minus cosine theta, that quantity squared. You could simplify more if you would like to, but it really doesn't matter. You're just figuring out whether your answer is positive or negative. And technically, like, you could factor out a negative here and make this cosine squared plus sine squared, but also don't go through the headache. It's not worth making a mistake with the simplifying when you know that you can just plug in your parameter. So if theta is equal to pi, if I plug in pi, cosine pi is -1, minus cosine of pi again is -1, but when we square it, it becomes a +1. Sine of pi is 0. In the denominator, we have cosine pi. Whoa, this should not be squared, that should be cubed. Sorry about that. Because we multiplied by the reciprocal. But now going back, cosine of pi is a -1. So 1 minus a -1 will give us 2. 2 cubed is 8. And we have -2a, great, -1/4. Really, we're concerned it's a negative. Therefore, our graph, or our curve, is concave down at when our parameter is pi. We do have to write the equation of our tangent line. Our parameter is when theta is equal to pi. We know that our slope is equal to 0. We still do need to have our point, though, in order to write this. So our point, if we plug in our parameter, we would have, our point would be, plug in our pi, we have pi minus sine of pi is 0. So pi minus 0 will give us pi. And our y value, we know cosine of pi is -1. So we have 1 minus a -1, which gives us 2. So our point is pi 2. And you could go through this if you get screwed up and say, I don't know what to do if I have, if my slope is 0. You could still use point slope form and things will simplify out for you. But knowing that your slope is equal to 0 and we have a horizontal tangent, well, now horizontal means that it's just going to be y is equal to, in this situation, 2. And you could, if you do get confused, again, like I said, you can go back to point slope. So this is what you can do with your derivative, which is pretty nice. Moving on to the next example here. And this is something I would star this one. This is probably the most complex problem maybe in this section. So parametric equations do not define y as a function of x. Well, basically, they don't have to be functions. So parametric equations do not need to be functions. Parametric equations do not need to be functions. Therefore, it is possible for a plane curve to loop around and cross itself, creating more than one tangent line at a given point. So you do have to graph these and see what you get. It makes it a lot easier, if it crosses, okay, well then I have two tangent lines there. So number 22. Keep that one in mind. So numbers close to this will be similar to this. Find the equation or equations of our tangent lines at the point where the curve crosses itself. Our parametric equation, x is equal to 2 minus pi cosine t. Y is equal to 2t minus pi sine t. Well, the first thing that I would do here is figure out, well, where does this cross itself? Otherwise, we just have our parametric equations. So we're over here on the right side. We'll write kind of a list of things in an order of what to do. So number one, we better find that point where the graph crosses. So number one, find the point where the graph crosses itself. Well, the easiest way to do this is obviously to graph it. So take out your graphing calculators and let's look at that. All right, so now have your graphing calculator out. And I'm still in parametric here, which obviously you have to be in parametric mode. And your x equation, 2 minus pi cosine t. Your y equation, 2t minus pi sine t. And then to check our window setting, this could take a long time to graph, and we can leave it from -10 to 10. That allows us to see anything negative with it. We should probably be okay. It does take a lot longer to graph. And again, if you don't see a point where it crosses, well then increase this t minimum and maximum, increase it, make it bigger because you just don't see enough of the graph. From -10 to 10 and from -10 to 10. So that's kind of our default still with our x and y's. And if we graph it, like I said, it could take a while here because there's a lot of t values that it has to evaluate. So what this graph, here we have our point. It really does connect over here. This is called a cardioid because it would continue, and a cardioid for your heart, cardio. If we made our x and y's larger, we could see it. But we do find the point where it crosses itself. And so here's our point. We may need to zoom in order to get a better idea. So I'm going to zoom in, and we can zoom in at 0, 0 because that's going to be pretty close to finding it. And again, these things just take a long time to graph, so you just have to be patient with it. And eventually you'll get it. So here is that point. So I would say our point is at 2, 0. And so for number 1, if we're answering the question, find the point where the graph crosses itself, well, I would predict that our point, or I would say that our point is at 2, 0. Number 2, we need to find parameter values. And really there are two of them. So if this is our point, what does this mean for our parameter? So number 2, find parameter values. And you're looking for 2 of them because we said it crosses itself twice. So when our parameter is at one value, we get the 0.20, and when our parameter is at another value, we also get the 0.20. So in order to do this, number 2, find the parameter values, we take our point. So here our point is 20, and we plug it in. So we're basically solving for that parameter, that t. So I have 2 is equal to 2 minus pi cosine t. Okay, well when I try and solve this, if I subtract 2 to both sides, that gives me 0 equals negative pi cosine t. And if we divide by negative pi, we get 0 is equal to cosine t. Well, we know that this happens many times. Usually you would want to start at 0 and go to whatever is necessary. But we know cosine, where is cosine equal to 0? Well, there's an infinite amount of answers there. So I would take, these are your principal values. Our principal values start at 0, and they would go around or go till there. So where is cosine equal to 0? That's at pi over 2 and 3 pi over 2. You don't have to use, like, let's say this one is really hard to solve. You could use your other equation. So we said, okay, well 2, because that's your x value, is equivalent to your x equation. If that's hard to solve, you can say, well, let's let my y value is 0. 0 is equal to 2t minus pi sine t. Well, in this situation, this one is really hard to solve for. I wouldn't really know where to go with this. Because I can't just divide it 2, because that's going to make it ugly here. I don't necessarily want to add this because I don't know where pi sine t is equal to 2t. So sometimes one of them is easier and the other one is hard. Usually you start with x's first just because x is your first value here in your point. But if the x one seems really difficult to solve for, try solving it in terms, of the y equation. But so this is the one, I'm not going to use it, and I don't need to use it. I found my parameter. For number 3, the third step though, we do have to verify the point given the parameter. So verify the point with the parameters found from number 2. So verify the point with the parameters found in number 2. So that's our third step here. Well, if t is equal to pi over 2 and 3 pi over 2, does that guarantee our point to be 20? So I usually, okay, if t is equal to pi over 2, if I plug it into my equation, I'm going to start on this side. Cosine of pi over 2 is 0. So times pi is 0. 2 minus 0 will give us 2. Now we need to plug in pi over 2 over here into our y equation. So if I plug in pi over 2, 2 times pi over 2 will give me pi. Maybe over here y is equal to pi minus pi times sine pi over 2. Well, sine pi over 2 is equivalent to 1. 1 times pi, obviously, is pi. Pi minus pi will be 0. So yes, when my parameter, when t is equal to pi over 2, I get that point 20, which is where the graph crosses. I also have to verify that 3 pi over 2 works. So if I plug in 3 pi over 2, cosine of 3 pi over 2 is equivalent to 0, times pi is 0, 2 minus 0 is 2. Plug it into the y equation. 2 times 3 pi over 2 will give us 3 pi. Minus sine of pi over 2, well, I'm sorry, sine of 3 pi over 2 is equivalent to negative 1. times a negative pi. So that will give me a positive pi. 3 pi plus pi is 4 pi. I think I did that right. Let me think for a second. So I have 2 times 3 pi over 2. That will give me 3 pi. All right. This obviously is not 0, and I did do this right. So what's ugly about this is, no, that point didn't work out. Well, what's another way to say 3 pi over 2? So I didn't, like in this situation, sometimes it's bad. Well, 3 pi over 2 is equivalent to negative pi over 2. And that's pretty ugly. I like it. Sometimes they'll give you the domain for it, so then you don't have this issue. Because here, obviously, the y value didn't work. So if I plug in negative pi over 2, cosine of negative pi over 2 is 0 times pi is 0. Well, that will give me 2. If I plug in my negative pi over 2 into this, sine of negative pi over 2, sorry, let me start at the beginning. 2 times negative pi over 2 will give me negative pi, minus sine of negative pi over 2 will give me negative 1, times pi will give me negative pi. Then if I add, negative pi minus a negative pi will end up giving me 0. That's kind of tricky in that sense there. And again, you might have to adjust that because we know that 3 pi over 2 is equivalent to the negative pi over 2. All right, so we found our parameter, we found our slope, we found our point. Now, number 4, we better find our slope. Well, we know we can get our slope from derivative. So for number 4, when we take our slope, we have change in y over to the change in x. Your change in y, if you can go up, we got to scroll up to see it, will give me 2 minus, keep the pi, that's a constant, derivative of sine is cosine t. Divided by our change in x, the derivative of 2 is 0, minus, keep our pi, the derivative of cosine is a negative sign, so that becomes a positive sine t. We know now that our parameter, that t is equal to pi over 2, and that t is equal to negative pi over 2. So we have to find the slope at these 2 points. So if t is equal to pi over 2, plug it in. Cosine of pi over 2 is 0 times pi is 0. That will give us 2 divided by sine of pi over 2 is 1 times pi will give us pi. So our slope is 2 divided by pi, which is kind of ugly. If we have our parameter at negative pi over 2, we also have to find the slope for that one. So negative pi over 2, that will give us 0 again for this term, times pi is 0. 2 minus 0 is 2. Divided by sine of negative pi over 2 is negative 1 times pi will give us negative pi. And oftentimes, these two things will be negative reciprocals of each other. So I have my parameter, I have 2 parameters, I have 2 slopes. The last step, number 5, is now we need to write our equation. Or equations, sorry. Because we know we have 2 of them. So up here, these are 5 steps. The last 2 steps tend to be the easiest. And get that all in there. But just a tedious problem here. So number 5, at the point 2, 0, if we have a slope of 2 divided by pi, again, I like to use the point slope form, that would give me y minus 0. Okay, well, that's y, equals my slope, 2 divided by pi times x minus 2. So in the long run, one equation is y equals 2 divided by pi x minus 4 divided by pi. We also know if we have the point 2 at the point 2, 0, we could have a slope of negative 2 divided by pi. Well, then y is equal to our slope, negative 2 divided by, sorry, it was y minus 0 again, equals our slope, -2 divided by pi times x minus 2. Therefore, y is equal to -2 divided by pi x plus 4 divided by pi. If we look back at our calculator, maybe this will turn on, maybe it's tired. In this situation, we know, and I wish I could write on here, we know that we have a tangent line that would go, this way. So that's your positive, that would be our first line. And we also have a tangent line this way. Hard problem. I think that's the toughest one in this section. A couple easy things left here, or with the derivative. If you have to find points where you have a horizontal and a vertical tangent, well, if you have a horizontal tangent, we know that means that our slope has to equal 0. Well, if our slope has to equal 0, that means that in your derivative, the numerator of your fraction has to equal 0. Well, our numerator is our change in y, so that has to equal 0. So if you have a horizontal tangent, that needs to happen. If you have a vertical tangent, you know that your slope is undefined. Well, if your slope is undefined, that means that in your fraction, your derivative, your denominator has to equal 0. So that means your change in x, that's in our denominator, that better be 0. So pretty basic stuff. And then, so number 30, find all the points, if any, of horizontal and vertical tangency to the curve. Use a graphing utility to confirm your results. Well, for this, usually I just say for horizontal, horizontal would mean my numerator, my change in y, has to equal 0. Well, our change in y will give us 3t squared minus 3. That has to equal 0. Pretty easy derivative to take. Solve for t. So that means if I add 3, divide by 3, that gives me 1. So t squared equals 1. Therefore, t equals plus or minus 1. If t is equal to a positive 1, well, I'm going to write down the negative 1, because they asked for points. So this gives us our parameter. A parameter is not a point. You have to take that parameter and plug it into your parametric equations to get the actual point for it. So plug in your 1, that will give you 1 minus 1 is 0, plus 2 will give us 2. Plug in your 1 minus 3, that's going to give us negative 2. So at the point 2, negative 2, you have a horizontal tangent. When our parameter is negative 1, plug in negative 1, we have 1, minus a negative 1 is 2, plus 2 will give us 4. Plug in a negative 1 cubed is negative 1, minus 3 times a negative 1, so that will end up being a plus 3. So we have negative 1 plus 3, that will give us 2. So these 2 points, we have a horizontal tangent. If we have to find a vertical tangent, our vertical would be where our slope is undefined, so the denominator, which is our change in x, where that is equal to 0. Well, change in x will give us 2t minus 1. Well, that's where t then is just, if we solve for it, it's a positive 1/2. There's only that one value. So if t does equal a positive 1/2, plug it in to get our point. Oh boy, 1/2 squared will be 1/4. Minus 1/2 will give us negative 1/4. Plus 2 will give us 1 3/4, which ends up being 7/4. Plug in 1/2 into the y's. That will give us 1/8 minus 3/8. No, minus 3/2, sorry. 1/8 minus 3/2 multiplied by 4. That will give us 12. That will give us 8. That should give us negative 11/8. So pretty easy to do that one. It's just that number 3 that's kind of a bear. All right. Now moving on to, we have other parametric in calculus. You might want to take a break right now, a stretch break. I'll try to find a good joke for you here. Take a break and come back in a minute. Well, I tried to get Boffman to come and be a motivational speaker to get you excited for the last two problems, but he's a bum and wouldn't do it, so make sure to give him a lot of grief. So we have arc length. Arc length, obviously with the arc length, we have a smooth curve C given by these equations. We already learned arc length, and we know that that deals with integration. So obviously this is how parametric equations deal with integration. We have our two equations, x equals f of t, y equals g of t. Your smooth curve, though, cannot intersect itself, except for possibly at your two endpoints, so where you start and stop. But it cannot intersect, and it shouldn't. But that is part of the rules here, that your curve cannot intersect itself except for at the endpoints. Your equation is very similar to the equation that you learned for arc length. So lowercase s, remember, indicates arc length. We're integrating from a to b, so that's your parameter that they're giving you. So a to b, and then it's the square root, which is very similar to our last equation, or to the rectangular equation for arc length, and it's the derivative of x squared plus the derivative of y squared, and this will be in terms of t. You can look for symmetry because that definitely helps. But super easy equation. You do have to have it memorized, but otherwise, really, it's not too bad. So the equation is simple. Sometimes some of the algebra in here, in order to simplify to integrate, can get a little bit ugly. Again, I'll probably make you show your work, but you can cheat by checking on your, it's not cheating. It's using your sources by checking on your calculator. So arc length, find the arc length of our curve over our given interval. It's in terms of our parameter, so -1 to 0. It is the square root of our x value, which is, the derivative of x, so 2t squared. So that will give us 4t squared. Oftentimes over on the side I just say, okay, x prime is 2t, then I can square it very easily. And y prime is equal to 12t squared. So if I square that, I have 144 t to the fourth. That's differential t. Looking at this, it looks like a bear to integrate, nothing simple, which we would like. And that was kind of common for arc length. There was a lot of things that just didn't work out great. Between 4t squared and 144 t to the fourth, you can factor out a 4t squared. And so sometimes if I make you do these things and say you have to show your work, well, obviously there's a way to integrate them. And this is a pretty common way. So then if I factor out the 4t squared, I'm left with 1. Plus, if I factor 4 out of 144, that gives me amazingly 36, which is great because it's a perfect square. Then I have t squared, differential t. And now, because you have multiplication, a property of radicals allows us to take the square root of the 4t squared. So we have -1 to 0. Square root of 4t squared is 2t. And then we have the square root of 1 plus 36t squared differential t. From here we can use substitution. So we know that we want u to be 1 plus 36t squared. And the derivative of u is going to equal 72t differential t. I already have a 2 here, so to get to 72, you can easily multiply that by 36. Otherwise, the old way that we did things is we said, okay, factor out a 2, multiply in the 72, and then obviously the reciprocal, but this works as well. So if I multiply in a 36, I better multiply by the reciprocal. Well, now my arc length, I have 136 from -1 to 0. 36 times 2t will give me that 72t differential t. So all of this is replaced with differential u, and we have the square root of u differential of u. Be very careful because I left the upper and lower bounds in terms of t. You can plug them in here and write them in terms of u, so it's your option again of what you would like to do. And it's a preference thing, so this one, because I wrote it, I'm just going to leave it in terms of t. Therefore, when I integrate, and this is obviously u to the 1/2, my u value, which is 1 plus 36t squared. Now that goes to the 3/2 times 2/3. And now from -1 to 0, so I have to go back in terms of t here. All right, to simplify, plug in your 0. If I plug in a 0, that's 0. 1 to the 3/2 will give me 1, times 2/3 is 2/3, times 136 is going to give me, I believe, 1/54. Fundamental theorem of calc, if I plug in a -1, oh boy, it's going to be ugly because I'm going to get to a 37 here. So -1 squared is obviously 1, times 36 is 36, plus 1 is 37. 37 to the 3/2 or to the power of 1.5 is just ugly. Multiply it by 2/3, and then multiply by 136 as well, or divide by 36. You can round to 4 decimals, because then this will be accurate to 3 decimals when you for your answer. So I have minus 4.1678. Well, if we look at this answer, we're obviously going to have a negative answer. So I have 1/54 minus 4.1678, and that gives me a negative 4.149. I think I rounded right. In this situation, obviously, we can't have a negative arc length. That doesn't make any sense. So for parametric equations, because you can get negatives, you have to take the absolute value of it. So your actual arc length is 4.149. And why you can have negatives is because if you're graphing this, your curve goes from right to left. So it's actually going, like, the curve of it's backward. Or I shouldn't say backward, but it's going to the left. So that's why you do get a negative value. So if you graph this just from -1 to 0, your curve is always working to the left, so you get a negative answer. In the long run, remember that arc length can't be negative. Take the absolute value. And so here you might want to say it is negative because curve goes from right to left. And then always take absolute value. So really not too bad. And yes, I'm going to let you do it on your own, but you can find that on your calculator as well, as you can go and calculate arc length even if you're in parametric. So one last thing today, we have our area of surface of revolution, and that always goes along with arc length, so it's pretty common that these two things are together. We have our smooth curve C, given by your equations, x equals f of t and y equals g of t. Again, it cannot intersect itself on the interval. So just like we had before, cannot intersect except possibly at your endpoints. We have from A to B, that's in terms of our parameter. Then the area S of the surface of revolution formed by revolving our smooth curve C about our coordinate axis is given by the following. Well, we have two situations, just like we had when we were dealing with rectangular. If you are if you're revolving about your x-axis, so obviously here's our x-axis. Capital S represents our area of surface of revolution. Again, this is 2 pi because we're revolving it. We're integrating from A to B, but that's in terms of our parameter. In this situation, now we have g of t. Well, g of t is equal to our y value, which is just what we had before. So it really, here, this is your y equation. Not much changes. Uh-oh, I better hurry. Your class is not done, I don't think. We do have to multiply by our arc length, just like we did in our last, when we learned it in rectangular. So the derivative of x squared plus the derivative of y squared differential t. So a pretty basic equation. Some minor changes from rectangular, but not too many. If you're revolving about your y-axis, now, well, area of surface of revolution, it's still 2 pi. You can still go from A to B. This time, we need f of t, which is obviously your x equation, because that is similar to your radius, what we dealt with before, times our arc length, so the derivative of x squared, plus the derivative of y squared, the square root of that all, differential t. So, pretty basic. Examples, we want to find the area of surface generated by revolving the curve about the x-axis and then be our y-axis. So for the first one, for A, x-axis, area of surface of revolution, so area of surface, so that's our capital S. Remember, we do have to have from 2 pi. We integrate according to our parameter, so 0 to 2. If you go about your x-axis, remember that means that you need your radius would be in terms of y. So that would be 4 minus 2t. Make sure you have parentheses around that. Times the square root of our arc length, so x prime will give us 1. 1 squared obviously is 1. Plus, we need y prime. Well, y prime is going to give us negative 2. If we square that, we get a positive 4, differential t. Well, this is really nice because this is just a constant which I can factor it out. Therefore, I have 2 pi times the square root of 5. This is all a constant. Integrate from 0 to 2, 4 minus 2t, differential t, and then we can easily integrate. So we have 2 pi, square root of 5, antiderivative would be 4t minus 2t squared divided by 2, so t squared. And again, this is 0 to 2, that's our parameter. So keep the 2 pi square root of 5, plug in your 2, that will give us 8 minus 4, oops, is 4, minus, plug in a 0, 0 minus 0 is 0, that gives us 8 pi square root of 5. You do letter B on your own. All right, so if you have the y-axis, you can take a lot of the information that you used from above, I guess, with your arc length, so you know you have the square root of 5. Y-axis, that would mean that you just need to have your x value here. Well, x is t. Remember, everything has to be in terms of t, and differential t indicates that for us. The integration is very easy. Answer, 4 pi times the square root of 5. So that's your parametric equations with calculus. And the last two sections, so sections 2 and 3, dealt with parametric equations. And moving on from here, the last 3 sections, 4, 5, and 6, will deal with polar. Here's your assignment. Good luck. It's all good stuff here.